every episode in this series reads one architecture as a bundle of assumptions. The earlier posts treated an architecture as a choice about which functions are even reachable. The convolution is different, and it is a good place to get precise, because it is the first architecture here that commits to a real symmetry. Of the data, start with a picture, just a grid of pixels. An ordinary linear layer would wire every output to every pixel, giving each one its own private weight tied to a specific position. A convolution flatly refuses to do that. Its first assumption is locality. A unit looks only at a small patch, a little 3x3 neighborhood, never the whole image at once. The bet is that the things that matter in an image, an edge, a corner, the stroke of a digit, are local. Nearby pixels belong together and can be read as a group. Pixels far apart can be handled separately later. So already, before any training, the layer has taken a strong position on what an image is.
But isn't that just a linear layer with fewer weights, an efficiency trick, nothing more?
That is the tempting reading, and it misses the real commitment. The second assumption is translation equivariance. The same patch detector runs at every position. Picture that one kernel sliding across the image. At each stop it lays the same weights. Over a new patch, multiplies and sums, and writes a single number into a grid we call the feature map. Slide it right, slide it down. The weights never change, only the patch beneath them does. So when you shift the whole input over, the output simply shifts with it. That is the equivariance. Translating the input just translates the result. And here is the part the efficiency story misses entirely. This is not a regularity the network slowly discovers from data and might later forget. It is a property of the operator itself, true at the very first step and still true after all the training. A feature learned in one corner is, for free, already known in every corner. That guarantee is the whole reason to give up the freedom of a dense layer. Let us look at what weight sharing actually means down in the code, because it is concrete and a little beautiful. This is the forward pass of a convolution written from scratch, no libraries, pure arithmetic. For every output position in the image, the inner loop reads the same kernel array. Indexed the same way each time, and accumulates the kernel times the patch sitting underneath it. Notice what is not there. There is no separate weight for the top left and the bottom right. There is one small set of weights, read again and again, exactly once per position. That reuse in the forward direction is not a detail of the layer. It is the entire layer. Locality and equivariance are not enforced by some extra rule. They fall straight out of this one act of reading the same weights everywhere.
And in the backward pass, why would sharing show up there at all?
Because one weight was read at every position going forward, its gradient has to be a sum over every position coming back. There is no way around it. A weight that influenced the whole output is answerable to the whole output. Watch the backward code. The very same kernel entry gets its gradient accumulated. A running total added up across all positions before you ever take a step. So weight sharing in the forward direction and gradient accumulation in the backward direction are one fact seen from two sides. How those gradients actually flow, the whole machinery of backpropagation, is its own from-scratch series coming later. Here we only need the shape of it. And keep an eye on that running sum over a shared axis, because it is a recurring character in this playlist. It comes back for recurrence, which shares the same weights across every step in time, and again for attention. Sharing a parameter always looks like this when the gradients return. Now the payoff, which is the reason anyone reaches for a convolution in the first place. A small convolutional network can match a much larger, fully connected one on a digit classification task, while using only a small fraction of the weights. Think about why the dense network is so wasteful. It has to learn, as separate facts, that an edge in the top left corner looks like an edge, and then all over again that an edge in the bottom right looks like an edge, once for every location an edge might appear. Every position gets its own private copy of the same lesson. The convolution learns the edge once, and reuses that detector everywhere. Far fewer weights, not because it is a smaller or weaker model, but because it refuses to pay for the same lesson in every corner of the image.
But fewer weights just means a smaller model. Isn't that simply less capacity?
It is less capacity spent on redundancy, which is exactly the kind you want to lose. And the real currency here is not weights at all, it is examples. Because the convolution never wastes data relearning the same feature in a new position, it can reach the same accuracy from far fewer training images. The dense network has to see an edge in every corner to trust it in every corner. The convolution only has to see it once. That is what an inductive bias buys you when it is true. Sample efficiency. You told the model something about the world in advance, so it did not have to spend precious data discovering it. The assumption did work that the data would otherwise have had to pay for. Matching a bigger network with fewer parameters is suggestive, but it is not proof. Maybe the convolution is just getting by, and the locality prior is along for the ride. So here is the honest test, and it is a lovely one. If a prior is really doing work, the way to find out is to break it. And watch the damage. Take the pixels of every image and scramble them with one fixed random permutation, the same shuffle applied to every single image, and then retrain both networks from scratch. The information is all still there. Not one pixel was thrown away, only moved. But to your eye, the digits are now pure noise.
Then both networks should fall apart the same way, shouldn't they? Same pixels, same shuffle.
That is exactly the intuition to test, and it turns out to be wrong. To the fully connected network, almost nothing changes. It treated the pixels as an unordered bag of features anyway, so a fixed relabeling of the inputs is invisible to it. To the convolution, the locality assumption is now a lie. Neighbors in the scrambled image are not neighbors in the digit, so a small kernel reaches out and sees an arbitrary handful of unrelated pixels. Its central bet, that nearby pixels belong together, no longer holds. The convolution's accuracy drops, and the dense networks barely moves. That gap is the measurement. The direction that the convolution is hurt more confirms the prior was real and load-bearing. The size of the gap tells you how much it was actually contributing. One honest caveat, so you are not surprised at the bench. On a small, pre-pooled digit set, where the preprocessing has already done most of the spatial work for you, the gap is modest. On raw pixels, it is large. The magnitude depends entirely on how much real structure survives into your inputs. But the method is the lesson, not the number. If removing a structural assumption costs you nothing, the model was never using it. That is what it looks like to measure an inductive bias, instead of just asserting one. So let us grade the convolution the way we grade every architecture in this series, on the same 3-row card. The bias. Space is local and translation invariant. Nearby pixels matter together, and a feature can appear anywhere. That is the assumption the layer hardwires. The win. Learn a feature once and reuse it everywhere, which is real sample efficiency whenever that assumption holds. You reach the same accuracy from far fewer examples. The bill. It breaks on global or scrambled structure, exactly where nearby pixels no longer belong together. The prior that saved you data on natural images becomes dead. Wait the moment the world stops being local. That is the whole bargain, and every card in this series has the same shape. A convolution is not a neutral, efficient layer that just happens to work well on images. It is a bet about images, baked straight into the architecture instead of merely hoped for. When the bet is right, you pay in fewer examples and you win. When it is wrong, you pay at exactly the edges you assumed away, and no amount of extra training buys back an assumption the operator made for you. Every architecture is a bet. This one bets on space.